Welcome to this video where we look at the integral control action as well as the derivative control action. We start with the integral control action. In my previous video, I've discussed the proportional control action, and we noted that the proportional control action for type 0 systems does not help in the improvement of the steady-state performance of the control system. We also noted that increasing the proportional gain constant helps reduce the time constant of the system and hence increasing the speed of response of the given system. However, because of its shortcomings in that we cannot increase the proportional gain constant infinitely because it is an amplifier and amplifiers have their saturation limits, and also because of the possibility of amplifying noise, then in some cases we will not be able to use the proportional control action. But for type 1 system, the proportional control action is able to improve on the steady-state performance of the control system. In this video, I will discuss the integral control action, and we look at its contribution in the control systems. The integral control action is as follows. The control signal is an integral of the error signal defined by U of t is defined by Ki, the integral of E of t dt, where Ki is the integral gain constant. Where Ki is the integral gain constant. Taking the Laplace transform for our equation, then we can write U of S is equal to Ki over S E of S, where the controller will now be defined by U of S over E of S is equals to Ki over S. That means when we have our control system as a negative feedback control system, the controller is defined by Ki over S, given the plant defined by the transfer function G of S, and the block diagram representation of the entire system with unity feedback will be as follows. So this is our controller defined by Ki over S. This is the plant under control defined by the transfer function G of S given unity feedback. Remember we said we test the system subject to a unit step input, and that means our R of S will be equal to 1 of S given a unit step input. We can proceed to test the operation of the integral control action on type 0 systems, and we'll start with type 0 first order system. The effect of the integral control action in a type 0 first order system. So the controller is defined by Ki over S, and the plant G of S is defined by 1 over Ks plus C, being a type 0 first order system. The open loop transfer function of the system will be obtained as Ki over S into Ks plus C, which will be equal to Ki over Ks squared plus Cs, from which the closed loop transfer function of the system will be equal to Ki over ks squared plus cs plus ki, which we can write as, we make the coefficient of s squared to be equal to 1. We divide by k on both the numerator and denominator to obtain ki over k over s squared plus c over ks plus ki over k. We can proceed to determine the steady state output of the system. The steady state output of the system will be defined or obtained by the limit as s tends to 0 of s multiplied by the closed loop transfer function, which is ki over k over s squared plus c over ks plus ki over k multiplied by the input r of s, which is 1 over s. And we notice that the s will cancel out. This will tend to 0, will tend to 0. We'll have ki over ki over k over k over k, which will be equal to 1. And therefore, the steady state response of the system for a type 0 first order system will be equal to 1. In other words, the integral control action is now able to improve the steady state performance of type 0 systems, which was a shortcoming with the proportional control action. We were not able to achieve a steady state output of 1 with the proportional control action, but with the integral control action, we are able to improve on the steady state performance of the given type 0 systems. And this is one of the major merits of the integral control action on the improvement of the steady state performance of the system. Now, it's also good to note that the closed loop transfer function of the system, denoted by or obtained as y of s over r of s, is defined by ki over k over s squared plus c over ks plus ki over k, can be compared to the closed loop transfer function of a second order system defined by omega n squared over s squared plus 2 zeta omega ns plus omega n squared. If we compare the two, we'll observe that omega n will be equal to ki over k square root, and also 2 zeta omega n will be equal to c over k, from which zeta will be equal to c over 2 omega n k, which will be c over 2, and then omega n k will be the square root of ki k. So this is the value for zeta, and this is the value for omega n. Remember, c and k are constants which depend on the system, and therefore the only parameter which can be varied here is ki. That means both omega n and zeta are functions of ki. If we wish to vary omega n, there is no way we can vary omega n without varying zeta, since both of them are functions of ki. And this is one of the shortcomings of the integral control action, in that it does not give the design engineer the flexibility of varying omega n and zeta independently. There is no way we can be able to vary omega n and zeta independently, since both of them are functions of the only parameter of design ki, and this is one of the major shortcomings of the integral control action. It is also good to notice that the control action is defined by ki over s. Introduction of the control action defined by ki over s is going to introduce a pole at 0 or a pole at the origin. Introducing a pole at the origin basically means that we are pulling the root locus of the system towards the origin, and that affects the stability margin of the system. In some cases, actually, the system may become unstable. And therefore, the second shortcoming of the integral control action is on the effect it has on the stability of the system. It affects the stability of the system negatively, pulling the stability of the system to the point of marginal stability of the system. And in some cases, depending on the nature of the system may actually become unstable. Because of those two demerits, the issue of non-independence in design of omega n and zeta due to only one design parameter ki, and the negative effect on the stability of the system, then the integral control action is not used on its own, but it is used together with the proportional and or with the proportional and derivative control action. And therefore, we do not use the integral control action on its own. However, we've noted of importance is that it affects the steady state performance of the system positively by improving the steady state performance of the system. And that is the integral control action. Lastly, I look at the derivative control action. The derivative control action. The derivative control action. The control signal is defined as a derivative of the error signal as u of t is equal to kd ddt of e of t. So the control signal is a derivative of the error signal. From this, we can observe that u of s will be equal to s kd e of s. And our controller is defined by u of s over e of s is equals to s kd. This is our controller defined by u of s over e of s is s kd. It's good to note that from the relationship between the control signal and the error signal, that when the slope of e of t is large at the current time, so if the slope of e of t is large, the magnitude of u of t will increase. So if the slope of e of t is large, the derivative of e of t is large, then the control signal u of t will increase. And that means that the derivative control law provides a large corrective action in anticipation before the error gets large. The derivative control action is going to provide a large corrective action in anticipation even before the error gets large. And this is the main advantage of the derivative control action. It has an anticipatory corrective mechanism on its own. However, we notice that if the error is constant, then the control signal will be equal to 0. If the error is constant, the derivative of a constant is 0, and therefore the control action u of t will be equal to 0. That means we cannot use the derivative control action if the error is constant or if the error is varying slowly. So we cannot use the derivative control action if the error is constant. And that is one of the shortcomings of the derivative control action. Number two, It's also good to notice that the control action is defined by SKD, and therefore the gain is going to increase with frequency. Remember, S is J omega. So if omega increases, that means the gain is going to increase, or the gain for the controller is going to increase with increase in frequency. And this has the effect of amplifying high frequency noise. So whenever frequency increases, that has the possibility of amplifying high frequency noise. And for those two reasons, the first one being that we cannot use the derivative control action when the error is constant or is constant. And number two, we risk amplifying high frequency noise. We do not use the derivative control action on its own, but it is used in conjunction with the proportional or with the proportional plus integral controllers. And for that reason, again, we do not use the derivative control action on its own. In summary, we notice that the derivative control action has an anticipatory capacity to be able to correct the error, and its shortcomings being the amplification of, or a possibility of amplification of noise, and we cannot be able to use it when the error is constant. And those are the advantages and disadvantages of the derivative control action. That is the end of my discussion of the integral and derivative control actions as used in control system. In my next videos, I will embark on the discussion of the proportional plus integral control action, the proportional plus derivative control action, and the proportional plus integral plus derivative control action. Otherwise, thank you so much for watching this video.